Good morning, everybody. Welcome to the last class day before spring break. Today is day 12. It's day 12. Let me see. No, it's day 14. All right. So today, what we're going to cover is Chapter 4, Section 2. Prime and composite numbers. All right. The difference between the two. Let's define those. So a prime number is any number that is only divisible by 1 and itself. For example, the number 2. If I divide it by 1, I get 2. If I divide it by 2, I get 1. I can't put any other number in there. 2 divided by 5 doesn't equal an integer. So they're only evenly divisible by 1. For example, and number 3. 3 is divisible by 1. 3 is divisible by 3. The number 4. 4 is divisible by 1. 4 is divisible by 2. And 4 is divisible by 4. Because of that, it's no longer a prime. It's now a composite number. Composite number is a number that has more than 2 evenly divisible factors. Remember what factors are. Factor is the product of 2 integers that equal another integer. So for example, 3 times 5 is 15. So 15 is made up of 1 and 15. That's what they equal. And 3 and 5. These are the factors. So 15 is made up of these numbers. And we call those numbers factors. 1 times 15 is 15. 3 times 5 is 15. So prime factors are the smallest numbers that make up a composite number. again. So 10 is made up of 10 times 1, also made up of 2 times 5. So the factors of 10 are 1, 2, 5, and 10. Because 1 times 10, 2 times 5 equals 10. So those are the prime factors. Take them down to its smallest numbers, because you take them down to as far as you can, and you'll end up with prime numbers. We use a method called the prime factorization tree. It's a diagram to keep track of all factors of an integer. Example, 48. Because 48 ends in an even number, we know it's divisible by 2. 2 goes into 4 twice, 2 goes into 8 4 times. So we know that 2 times 24 is 48. That's a prime number we can refer. But 24 can be broken down. Since it ends in an even integer, we know that it's divisible by 2. 2 goes into 2 once, 2 goes into 4 twice. So 2 times 12 is 24. 2 times 12 times 2 is 48. We can keep on going down until you can't break a number down any further. 12 is made up of 2 times 6. 2 times 6 is 12. 2 times 12 is 24. 2 times 24 is 48. So that's a prime number. 6 is made up of 2 times 3. And these are both prime numbers. So 48 is made up of 2 times 2 times 2 times 2 times 3. 1, 2, 3, 4 times 3, which means 48 is made up of these numbers. Again, any number can be broken down to a series of prime numbers, which gives us our first theorem. Instead of writing theorem, I'm simply going to use the abbreviation THM. This first theorem is called the fundamental theorem of arithmetic. What it says is, for every composite number for any or every composite number, they can be written as a product of prime numbers. Or you should say every composite number can be written as a product of prime numbers. But they can only be written in one and only one way. This is the fundamental theorem of arithmetic. For every composite number, they can be written as a product of prime numbers in one and only one way. Order is not important. In other words, 2 times 3 is the same thing as 3 times 2. They both equal 6. So it doesn't matter how you arrange them. It'll give us the same thing. And we just proved it, actually. Help here in number 4, in the example of 48. 48 can be written only in this way. 2 times 2 is 4, times 2 is 8, times 2 is 16, 16 times 3 is 48. There's no other way. I can't put any different numbers in there. All right, so that's the fundamental theorem of arithmetic, that we could break down any number into its prime number divisors. This next part, we're going to talk about every factor of an integer is also a divisor of that integer. Every factor of an integer is also a divisor of that. So its divisor means can divide that integer. Let's look at the number 30. It's made up of 3 times 10. 3 is a prime number, can't go any further, but 10 is a composite number. It's made up of 2 and 5. So the factors of 30 are, these are the factors. Every number always has 1 and itself. But besides 1, we have 2, 3, 5, and 30. So these are all the factors of 30. They're not prime factors, they're just factors of them. What it says here then is any one of these numbers, I could take 30 and divide it by 2, I get 15. That's an integer. That's good. I get 30 divided by 3, I get 10. That's an integer. I get 30 divided by 5, that's 6. That's an integer. And any combination of these, if I multiply 2 times 3, I get 6. 30 divided by 6 is 5. That's an integer. So any combination of these products, as long as they're not larger than 30, is also factors. They're divisors. I should say not factors, divisors. So any factors are also divisors. They fit into that number evenly. And here's a theorem that says this. If a number D is a divisor of n, where n does not equal 0, then the number n over d is also a divisor of n. So we've looked at a divisor. We could say they're similar to factors. So if we factor something, we know we had 30 is 1 times 2 times 3. So as we did up here, we had, here's a number. 30 divided by 2 is 15. This is the n over d. Since these are all divisors, these are all d's. N over d. This is n. These are my d's. So 30 divided by 2 is 15. That means 15 is also a divisor of 30. And 15 is made up of 3 times 5. Or let's look at, if we take 30 divided by 3, this is my n, this is 30, d is 3, that equals 10. Which means if I take 30 and divide it by 10, I get 3. And 10 comes from 2 times 5. So this is what the theorem means. Now, let's find the number of them. I had the yellow lines up there. All right. Finding the number of divisors. Example, let's start with number 24. What's 24 made up of? It's an even number, so we know 2 goes in there. Because the last number is 4. 2 goes into 4. 2 goes into 2 once, 2 goes into 4 twice. That's a prime number. 12 is made up of 2 times 6. 6 is made up of 2 times 3. So 24 is made up of 2 times 2 times 2 times 3. Which makes it 2 to the third times 3 to the first. Because there's only 1 3 and there's 3 2s. So far so good? Because now we're going to use these numbers individually and then together to tell us how many numbers we can have. Here's a note. We have to remember this. Anything to the power 0 is 1. Any number to the power 0 is 1. So this is when we create a chart. This is our number. These are my exponents. So the number is 2. In this one, I have all the way up to 3. So I can have 2 to the power 0 equals 1. 2 to the power 1 is 2. 2 to the power 2 is 4. And 2 to the power 3 is 8. 2 times 2 times 2. Let's look at the number 3. We have 3 to the 0, which is 1. And we only have 1 3. There's only 1 3, so it's 3. So those are all individual ones. Now we combine them. We have 2 to the n times 3 to the m. If 3 is 0 and 2 is 0, 1 times 1 is 1. If 3 is 0 and 2 is 1, this is 1 times 2 is 2. If 3 is 0 times 2 to the second, that's 4. If 3 is 0 and 2 is 3, it's 8. So that's all of them with 3 to the 0 power. How about 3 to the 1 power? 3, we did that. So 3 to the first times 2 to the first is what? Because we have 3 to the 0, 2 to 0 already. So 3 to the first, second to, so 3 to the first is 3, 2 to the first is 2, so that equals 6. Three to the first times 2 squared. 2 to the second power is 4. 4 times 3 is 12. 3 to the first times 2 to the third. 2 to the third is 8 times 3 is 24. These are all the factors possible. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different combinations, but all of these are the same. That was the same. That was okay. That one's okay. These are the same. So we can determine how many we have. These are all the different combinations, but the only possible factors we have are 1, 2, 3, 4, 6, 8, 12, and 24. 1 times 24 is 24. 2 times 12 is 24. 3 times 8 is 24, and 4 times 6. Those are all the possible combinations. Which brings us to 2 more theorems. For example, if P and Q are prime numbers, and N and M are whole numbers, then P to the power N times Q to the power M has N plus 1 times M plus 1 whole number divisors. If P and Q are prime numbers and M and N are whole numbers, so we're P to the power N. So these are the prime numbers. This is how many times they occur. Let's look at our example here. 24. We know it equals 2 to the third times 3 to the first. This is our N. This is our M. So according to this first, we have 3 plus 1 times 1 plus 1. 4 times 2 equals 8. What does this tell us? 8 number of divisors. Our 24 has 8 number of divisors. Or I should say has 8 divisors. However we want to put that makes sense to you. I was going to say one way, but then I changed it because the number 24 has 8 unique divisors.
Yeah, I think that.
Okay, and we proved it already up here.
Okay.
1, 2, 3, 4, 5, 6, 7, 8. That's what it tells us. So we know how many we're going to have. That's what that theorem tells us. Let's look at another example. $1 million. And if we have an exponentiated number. How many divisors will these numbers have? Actually, we could, but in this one's pretty easy. Because whenever you have a 1 and a bunch of zeros, we know it's a factor of 10. So it's a factor. You could, yeah, because you could do 10 times 100,000. 10 times 10,000 is, and keep on going from there. What you end up with is, since it's 10, 1, 2, 3, 4, 5, 6. This is the same thing as 10 to the 6. 10 times 10 times 10. Using our theorem, remember, we have to have P and N and Q and M, where P and Q have to be prime numbers. Is 10 a prime number? No. So what we have to do now, what is 10 made up of? Yeah, so we have to go down to make those into prime numbers. And one of the rules of exponents, if you have a multiplication, here's the rule of exponents. If you have a product raised to a power, you can just distribute that power to everything inside there. So there's this power goes to both 2 and 5. Now we have that. Now we're supposed to be in, with respect to that formula. So N is 6, M is 6. We need N plus 1 times M plus 1. So 6 plus 1, 6 plus 1. So 1 million has 49 unique factors. Okay, let's look at the next one. 210 to the power 10. 210 is not a prime number because it ends in a 0. So we know that 210 can break down into 21 times 10 because it ends in a 0. 21 breaks down to 3 times 7. And 10 breaks down to 2 times 5. So 210 to the power 10 is 3 times 7 times 2 times 5 to the power 10. Take this exponent and distribute it to everybody inside there. 3 to the 10 times 7 to the 10 times 2 to the 10 times 5 to the 10th. So this is P, Q, R, S, M, N, O, P, whatever. So to find the number of divisors, take our exponents, add 1. 10 plus 1, 10 plus 1, 10 plus 1, which is 11 times 11 times 11 times 11, which is 11 to the 4th. Which I did that, it was 14,641. So you break down the number down to its farthest prime number sets, whatever exponent you had on the original, just push it over. How about if we had something like this? Two times two, yes. Which becomes
Then you do, this one and this one. This one is good.
which is 81. And you notice you have to have two numbers. You have to have a P and a Q, even if they're the same. Because what we look at here is 2 times 2 is also 2 squared. When you have a power to a power, you multiply. 8 times 2 is 16. If you just have 1, what it's going to give you is 16 plus 1 is, this one says we only have 17 combinations. But according to that is, we have the other one. All right, let's look at the other theorem. So that was the theorem. If P and Q are prime, okay, yeah, if P and Q are prime numbers, let's look at another theorem. If N is a whole number, greater than 1, in other words, it has to be a counting number. It's a natural number. And N is not divisible by any prime number such that P squared is less than N. If that's true, then N is a prime number. So if N is a whole number, what's a whole number? A whole number is any number from 1, 2, 3, all to infinity. But this is greater than 1, which is the natural numbers minus 1. The reason 1 is a universal number, so this wouldn't matter. 1 is automatically a prime number. N is not divisible by any prime number such that the prime factors, if I square them, they're going to be less than the number I'm looking at. Let's look at this. For example, 4 breaks down to 2 times 2. 4 is my N, the 2's are my P's. according to this, my p's, if I take 2 and square it, is it less than equal to 4? Yeah, so now let's look at 6. If n is 6, if 6, it's made up of 2 times 3. So these are my n, those are my p's. I can look at both of these p's. Is 2 squared less than equal to 6? Yes. How about 3? Is 3 squared less than 6? 3 squared is 9. No. So therefore, 6 is not a prime number. This is how you can tell. I don't know if it's supposed to be equal to, I think it's supposed to be strictly less than. It should be strictly less than. Because 2 squared is, this one says if that's true, then 4 is a prime number. And we know it's not a prime number. So I think it should be, that's miswritten. Okay, here's some examples. A is 397 and B is 91. So 397 breaks down into what? Well, let's look at the numbers. Let's look at the first series of prime numbers. Let's look at all the prime numbers. 1, 2, 3, 5, 7, 9, 11. Because we have to go all the way until p squared is less than n. 11 times 11 is 121. We just have to go further. The next one is 13. 13 times 13 is 169. Then 17, 19 plus 20, 20 is 400. So it has to be up to 19. What we have to do here is this. We have to look at which one of these satisfy that condition. Remember what this means from last class? No. It means n divided by p. Or you divide it. So besides 1, does 2 go inside 397? No, since the last number is 7, 2 doesn't go in there. In other words, if I took 2, I couldn't get a whole number there. So 2 is not divisible. How about 3? What's the rule for 3? If I add up these numbers, is it divisible by 3? 9 plus 3 is 12, plus 7 is 19 divisible by 3? No. Is it 5? Is the last digit a 5 or a 0? No. Since it's not divisible by 3, it's not divisible by 9. The way you can tell by 9 is if you add up the numbers and that number is divisible by 9 also. Same thing as 3. Is it divisible, not by 7, is it divisible by 11? No, because 11 times 11 is 121. 121 times 11 is bigger than 1,000, so that's not. Same thing with 13. 13 times 13 is 169. So 169 times 13 is going to be bigger than that. So since it's not divisible by any of the first prime numbers, all the way up to p squared being less than or equal to 9, then that means this is a prime number. Let's look at 91. Here are all the possible p's we can use. 1, 2, 3, 5, 7, 9. we can't go any higher than 9 because 11 times 11 is 121 can't be bigger than this. This is my n. So does, yeah, 1 goes in there, but we can't use that. Does 2 go into 191? No. Does 3? No, because if you add up 9 plus 1 is 10. No. Is 5? No, no, because if it's divisible by 5, it would end in a 0 or a 5. So it's not 5. 9 times 9 is 81, so it doesn't go in there. The only question we have is about 7. Does 7 go into 91? 7 goes into 9 twice. No, it goes in once, I'm sorry, once, so it's 7. 13. Yeah, well, and then that gives you 13. Well, I said twice. 7 goes in 9 once, and then so 7 times 13 equals 91. So 91 is not a prime, it's a composite. That's what that second theorem tells us, is we can look at all those individually. Kind of what we just did here. It was first discovered something similar to that by a guy named Eratosthenes. He was a Greek philosopher, mathematician, physicist, scientist. This guy here, in the years like 61, it's like 2,000 years ago, he determined that the Earth was round, and the circumference of it and the diameter of it, he got it accurate to a few degrees. This is way before paper, way before pencils. This guy figured out that the Earth was round. Here, well, how he did it was very interesting. In Egypt, in the town called Alexandria, Eratosthenes noticed that at one tunnel where he was standing, the water well, at one day, each year, the sun is directly above you twice in a year, at the vernal and autumnal equinox. That's when the days and nights are equal distance, equal length. So the sun is directly overhead. What he did, he noticed that on that day at noon, there was no shadow in this tunnel. But he also had a friend of his at the same time look at his water well and notice that there was a shadow in there. And this is, of course, a good distance away from Alexandria to wherever he was. And he noticed because of that, the shape of the shadow inside that well, he determined that the angle of it, here's the well, and the shadow was like this. So he determined that the angle of the Earth had to have been that degree. So he determined, since the Earth was not flat, it had to have a bend and that degree. So he determined how big. I mean, this guy was so far advanced of himself. But that's a guy named Eratosthenes. He developed on this. It's called the sieve of Eratosthenes. A sieve is like a silo. If you throw in all your prime numbers, and whichever's don't work, throw them away. What you're left with is an answer, like we did here. We got rid of 1 by 1, and this guy thought about this back 2,000 years ago. That we can find prime numbers that make up anything by looking at each one separately. If it doesn't work, get them out. Whatever's left are our composite numbers. Genius. Is the number of prime numbers finite? all the numbers. You want to say yes, why?
Because they're always gonna be that.
That's an interesting question. You think, because numbers are infinite, there's got to be an infinite number of prime numbers too. Because if we look at it, this is called the infinite. I say infiniteness, infinitude of prime numbers. The infinitude of prime numbers. Oops. We start off with 1, then 2, then 3, then 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and so on and so forth. But you see this? These are all pretty close together. This is 3 numbers apart, 2 numbers apart, 4 numbers apart, 2 numbers apart, 4 numbers apart, 6 numbers apart. So because of that, between the other next prime numbers, it gets bigger and bigger and bigger. What I'm getting to is, how can we prove that there are, say, 1 million of them? But no, because of that, because there's no repeating pattern, it's going to happen. There's got to be another prime number out there eventually. So that's about the infinitude of prime numbers. Because since the numbers never end, we don't know exactly where the next prime number is going to be. There comes to a point where they start getting further and further apart. Let me see. I will. Do we have time? We're in chapter 4. You're taking forever. I believe there's only one more section in chapter 4. And if we could finish it off before spring break, then you guys could try to finish that up. Oh, okay, great. Yeah, okay. Chapter 4, section 3. Greatest common denominator or divisor. GC, what do they call it? Oh, yeah, divisor. Yeah. And then least common denominator. Okay, this is called GCD. The GCD, what do you think that defines as? What do you think that means? Not the number, divisor. Which means what? Yes, you just told me the answer is the question. You were going to say
The largest number that you can divide.
Yeah, the largest number that goes into 2 numbers equally, or factors of 2 numbers. Largest number that evenly divides two numbers. Let's look at these two numbers, 15 and 30. So what are the divisors here? Right? We have to look at all of them. So 30 is made up of 1 times 30, 3 times 10, 2 times 5, 6 times 5, 15 times 2. So any combination of those. What's the greatest common divisor then? Does 15 go into 15? Yes. That's that one. So break them up to pieces and see what the largest one is. The least common denominator. It's one more time what?
Smallest number.
No. It is the smallest number, hence least common. It's what number, what's the smallest number that both of these numbers fit into? Both of the numbers fit into. For example, 24 and 16. 24 is made up of what? 2 times 12, 2 times 6, 2 times 3. So it's 2 times 2 times 2 times 3, which is 2 to the third times 3 to the first. I prime factorized it. And 16 is 2 times 2 times 2 times 2, which is 2 to the fourth. So what's the smallest number that both of these numbers fit into? It's got to be, they have to fit into, so it has to be bigger than 16. 2 fits into it. 2 is the smallest denominator, divisor, but the least common denominator is what's the smallest number that both of these numbers fit into. Has to be bigger than these, because if you look at it, 24 and 16, 24 times 1 is 24. 24 times 2 is 48. 24 times 3 is 64. So this is 1, 2, 3, 4. 24 times 4 is 96. 24 times 5 is 120. And 16 times 1 is 16. 16 times 2 is 32. 16 times 2 is 48. 16 times 4 is 64. 16 times 5 is 80. Right. Now, how do we find that? With this. Since the top one only had 3 2s and the bottom one had 4, I use this one. Since this one had 1 3, this one didn't, I use that one. So if I took 2 times 2 times 2 times 2 times 3, I get 48. So when you factor them, look for the largest exponent. If they're even, if the number is missing, if the number is missing, then that number is automatically in the list. One more. Okay, so we have 12 and 60. What is 12 made up of? 6 is a composite. 6 is made up of 2 times 3, so 2 times 2 times 3, which is 2 squared times 3 to the first. 60 is made up of 2 times 2 times 3 times 5. Two squared, 3 1 5 1. You shouldn't have to look at the board because I mean you should be able to break down 60. 60 is 2 times 30, 30 is 15 times 2, 15 is 3 times 5. So you have to keep bobblehead. You should be able to do that yourself. Practice those. Now, what's my LCD? Let's look at the 2s. How many 2s can I use? 2. So that takes care of those. How many 3s? Anything else? Yeah, because there's a 5 here. So 2 squared is 4. 3 to the first is 3. 5 to the first is 5. 4 times 5 is 20. Times 3 is 60. The smallest number that both of those fit into is 60. That's how you do it. Okay, that's the end of chapter 4. So try to catch up on your homework and finish your test up until chapter 4. When we come back, we're going to start chapter 5. How many more chapters we have? We're going to chapter 8. So when we come back, we only have 4 more chapters left in 8 weeks. So we'll cover a chapter every 2 weeks. All right, that's it for today. Have a great, safe vacation. And